Assalamualaikum warahmatullahi wabarakatuh and a very good morning everyone. So this will be the last chapter for this subject, Engineering Mathematics 2, which is partial differential equations or known as PDE. So this is the contents of this topic. The first one, you will be introduced what is PDE, and then what is the basic concepts in PDE, and then it follows by the application of PDE, which is heat equation, wave equation, and Laplace equation. And the last one is how to solve PDE using the Allenby's solution. In the previous topic from chapter 1 to chapter 6, you have learned about ordinary differential equation or ODE, where this ODE can model simple physical system. But what about modeling complex systems, especially in fluid mechanics, heat transfer, and electromagnetic theory, or any other complex application? So all these problems can be modeled by using partial differential equation or PDE. Before we go deep into what is PDE, first let us understand what is the function of several variables. Okay, let's say we have a thing of cylinder. We know that the volume of the cylinder is given as pi r square h, where r is the radius and h is the height of cylinder. Okay, from this formula, we know that pi is a constant. Okay, and we know volume, or we can write it as V, depends on r and h, depends on these two variables. Okay, if the radius of the cylinder is changing, meaning that it's either increasing or the radius is decreasing, there is no change in height. Same goes if the height is changing. Okay, let's say the height is increasing or the height of the cylinder is decreasing, there is no changes in R. Okay, we can say that R and H are the independent variables, meaning that the changes in R does not affect the height, and the changes in height does not affect the R. But the changes in R or H will affect the volume of the cylinder. So V is considered as dependent variable. If the radius or height is changed, the volume of the cylinder will also change. So if we want to know the rate of change of the volume of the cylinder with respect to radius, we can treat h as constant, and this can be expressed as partial derivative, where we write it as del V over del R. And if we want to know the rate of change of volume with respect to height, the partial derivative of this will be del V over del H, where R here will be constant. Partial differential equation contains partial derivatives, or we can write it as del, of a function of two or more independent variables. Let's say we have a function of z in terms of x and y. So x and y are the independent variables and z is the dependent variables. From here, we can find the first order partial derivatives with respect to x, where it is the differentiation of z with respect to x. Or if we want to find the first order partial derivatives of z with respect to y, we can write it as this. We also can write the partial derivative as z sub x or z sub y. Okay, the second order of partial derivatives with respect to x is written as del squared z over del x squared. And the second order partial derivative of z with respect to y is written as del squared z over del y squared. Or we can write it as z sub yy or z sub xx. The last one is the second order of the partial differential with respect to x and y, meaning that we will differentiate z with respect to x, followed by the differentiation of dz over dx with respect to y. Or we can write it as z sub xy. And this is the second order of partial derivative with respect to y and x, or we can write it as zyx. Now, how we want to identify the types of PDE? Okay, first we will go how to know the order of the PDE and how to know that the PDE is linear or nonlinear. And the last one is we want to know if the PDE is homogeneous or non-homogeneous. Okay, so now the first important term is the order of PDE. How do we want to know the order of PDE? Okay, we can know the order of PDE by taking the highest partial differential coefficients occurs in the equation. So the highest partial differential coefficients will be the order of the PDE. So for this case, for the first one, where this is del u over del t equals to u squared plus del u over del x. So here we have two partial differential coefficients. The first one is the first order, and the second one is also the first order of partial differential coefficients. So the order of PDE is equals to 1. Okay, the next example is given this equation. So we have two partial derivative, which is ux, and the second one is uy. So this is the first order of partial differential coefficients, and this is the first order. So the highest order of the equation is 1. Okay, the next one is uyy equals to this. So we have 1, 2, 3, and 4 partial differential coefficients. The first one is the first order type. The second one is also the first order. And the third one is the first order. And the last one is the second order. So the order of PDE is equals to 2 because the highest partial differential coefficient is 2. Okay, now let us discuss how to determine if the PDE is linear or nonlinear. A PDE is linear if the first condition is the power of dependent variable and each partial differential coefficient contained in the equation is 1. So the power must be 1. And the second condition is the coefficients of the dependent variable and the coefficients of each partial differential coefficients are constants or function of independent variables. So the second one is the coefficients must be constant or functions of independent variables. If any of these conditions is not met, then the PDE is nonlinear. Okay, let us try the first example. Given the equation is del u over del t equals to del squared u over del x squared minus u. So the dependent variable here is u. So for the first condition, the power of dependent variable So the power of the dependent variable for here is 1, and this is also 1, and the power of dependent variable u is also 1. So here, for the first condition, it is satisfied. So let us check for the second condition. The coefficients of the dependent variable must be constant or function. So we can see that the coefficients of the partial differential coefficients here and here is equals to 1, and the coefficients of u is also equals to 1. So it fulfills the second conditions. So this means that this partial differential equation is linear PDE. Okay, the second one is del square u over del t square equals to u square plus del square u over del x square. So first we check the first condition where the power of the dependent variable must be equals to 1. So if we notice here, the power of the dependent variable is equals to 2. So it means that the first condition does not meet. So it is a non-linear PDE. Okay, now we proceed with the third example, where given this is ut equals to ux xy. Okay, the first one is the power. The power of dependent variable is 1, so it is satisfied. And the second condition is the coefficient of the dependent variable and the coefficients of partial differential coefficient. Okay, if you notice here, the coefficient of uxxy or the partial differential coefficients is not constant, but it is dependent variables. So we can say that the second condition is not met. Therefore, this PDE is non-linear. Okay, now let us discuss on how to identify that the PDE is homogeneous or non-homogeneous PDE. So a PDE of any order is homogeneous if every term of the PDE contains the dependent variable u or one of its differential coefficients. If it's not satisfy any of this, it is called as non-homogeneous PDE. Okay, now let us try this example in order for you to understand more about homogeneous and non-homogeneous PDE. Okay, for the first example, we go through for every term. So the first term, it is the partial differential coefficients. The second term is also the partial differential coefficients. The third one is the partial differential coefficients, and the fourth one is the partial differential coefficients. So it means that all the terms in the equations contains the partial differential coefficients. So this is a homogeneous PDE. For the second one, the first term is the partial differential coefficients, and this is also partial differential coefficients, and the last one is the dependent variables. So this, since the terms, all terms contains the dependent variable and the partial differential coefficients, so this PDE is also homogeneous. The last one is this equation, ut equals to USS plus x. So the first term is the partial differential coefficients, and the second term is the partial differential coefficients. But the third term does not contains the dependent variable or the partial differential coefficients. So we can say that this is a non-homogeneous PDE. Okay, we have learned how to find the order of the PDE, and does the PDE is linear or nonlinear, and also does the PDE is homogeneous or non-homogeneous type. Okay, now we want to discuss is does the function of U is a solution of PDE, and if the function is a solution of PDE, it should satisfy the equation under the discussion, and also it should satisfy the given condition as well. Okay, in order to understand this concept, let us try this example. Okay, show that this solution of U is a solution of ut equals to uxx. Okay, now we have the function of u in terms of x and t. So in order to know that this function is a solution of ut equals to uxx, then you have to substitute the differentiation of u into this equation. So first you have to find the differentiation of u with respect to t, where you have to differentiate this function with t. Okay, so for x, when you differentiate x with respect to t, it will be equals to 0. And then you differentiate e minus t sine x with respect to t, you will get e to the power of negative t. Then you have to differentiate negative t with respect to t, you will get negative 1. And then sine x will consider as constant because this function of sine is in terms of x. Okay, now we have the solution of ut. Then we try to find the differentiation of ux, where this will be del over del x, x plus e to the power of negative t sine x. Okay, now we can solve the differentiation where we get 1 plus. So this exponential is in terms of t, so we consider it as a constant. So e to the power of negative t, and differentiate sign, you will get cos x. Okay, then you differentiate the ux with respect to x again to get the second order of the partial derivative. So this will be del over del x 1 plus e to the power of negative t cos x. So differentiate this, you will get e to the power of negative t, and differentiate cos, you will get sine x negative. Okay, then we can know that the left hand side, which is ut, is equals to negative e to the power of negative t sine x, and the right hand side, which is uxx, is equals to negative e to the power of negative t sine x. This means that the left hand side is equals to the right hand side. So it means that the solution u is the solution of this equation. Okay, for this question, they gave you the solution of the PDE, and you have to show that this function is the solution of this equation. But what if they only give you this equation and you need to solve this to get the value of uxy? So in order to solve this, you really need to have the condition, which is called as boundary condition or initial condition, in order for you to solve the solution, in order for you to get the solution of this equation. So what is boundary condition? A boundary condition is the conditions that a solution assumes given values in a bounded domain, which means that it provides information at the end of the domain. So for this case, we have two cases. For the first one is rod, and for the second one is rectangular plate. So I give you two examples. Okay, given the rod, where the length of this rod is equals to LCM. So the boundary condition is when the condition is at the end of the domain. So it means the first one is here, and where this is when x is equals to 0, and the condition is when x is equals to L, which is the end of this rod. So given the condition is when x equals to 0, the value of u is equals to alpha, and when x is equals to L, the condition u is equals to beta. Okay, so for rod, we have two boundary conditions. Okay, now we see for rectangular plate. For rectangular plate, we will have four domains. The first one is this one, when x is equals to 0. And the second one is when x is equals to L1. Because why it is L1? Because the length of x is equals to L1 cm. So we can write it as x L1 equals to L1. And the third domain is when y equals to 0. And the fourth domain is when y is equals to L2, because the length of y is equals to L2. So we have four boundary conditions for rectangular plate. Okay, another conditions that is important is initial conditions. This initial conditions is very important, especially for the heat equation and also for wave equation, because these two equations involve parameter time. So you really need to have the initial condition, where the initial condition is the condition at an initial time where t is equals to 0, or we can say it as the starting time.